Good day everyone and welcome to these lectures on physico-chemical processes for wastewater treatment. So, we will be continuing this our discussion or knowledge sharing with respect to reverse osmosis. So, in the previous lecture we started understanding the reverse osmosis process, which is used a lot in for water treatment in different industries as well as in the households. So, we tried to find out the basic equations of reverse osmosis, understood osmosis as well as reverse osmosis in the previous lecture. Continuing further, today we are going to learn regarding the properties of RO membranes, as well as we will try to see that what are the different variables which affect the RO process in detail. So, membrane materials, the materials most widely used in the RO are like cellulosic derivatives or polyamide derivatives. So, these are very common materials which are used as RO membrane material, and cellulose acetate, the most common commercial material which is used in the membranes for RO, is not tolerant to temperatures above 30 degree centigrade and tends to hydrolyze for the pH range which is beyond 3 and 8. So, this is the common issues which are there with respect to cellulose acetate. Also it is susceptible to biological degradation and degrades when free chlorine concentration above 1 milligram per liter is there. So, this is another problem with respect to cellulose acetate. Now, polyamide membranes are more resistant to biological degradation, and also they are stable beyond the pH range of 3 to 11, and they do not hydrolyze in water as well. So, in this way polyamides are better as compared to cellulose acetate. Under similar pressure and temperature conditions, polyamide membranes can reduce higher water flux and higher salt rejection than the CA membranes. So, again the PA membranes are better, but PA membranes are more susceptible to fouling and cannot tolerate free chlorine at any concentration. So, this is the harmful or disadvantage with respect to PA membrane. Now, there are many configurations which are possible, and previously also for overall membrane nanofiltration, ultrafiltration, microfiltration also we have studied these membrane configurations. So, again for RO membrane configuration, the units are fabricated in either spiral wound configuration or hollow fiber configuration. So, both of these are common. Now, two sheets of flat sheet membranes are joined along with the three sides with the active membrane layer facing out. This is also there. The spacer is placed between the membrane sheets to keep them from touching. So, this spacer is used here. Now, open end of the envelope formed by the two sheets is attached to the perforated central tube that collects the permeate. So, this is how the membrane configuration is there. Now, the spiral wound elements are typically 1 meter long and 0.3 meter in diameter. So, this is there. This is the typical configuration of spiral wound element. Now, the area for 1 meter long element will be typically 30 meter square. Individual elements may have permeate recovery of 5 to 15%. To achieve higher recoveries, these may be placed in series also, and typically 4 to 7 elements are arranged in a series in a pressure vessel. So, this is how the recovery rates are increased. Now, this is a cutaway view of spiral membrane module you can see here. So, these are the different. So, source water we can see here, the permeate will be coming out from here, the concentrate will be coming out from here, okay, and the permeate flows through the porous material in the spiral path which is there, and you can see here the these pores which are shown here. The source water entry will certainly from this side and from this way, and within these membranes the separation will happen. There are different sections you can see here, the source water, the membrane cast on the fabric backing, then porous permeate carrier also. So, there are different sections within the spiral membrane module which are shown here. So, we can understand little bit better if we can actually see the any membrane module nearby to our place where we are living. So, we can go in the industry also, these are very common modules which are used. Hollow fiber element has several thousands fibers with outside diameter on the of the order of 0.085 millimeter suspended in a pressure vessel. The permeate recovery is about 30% for each element, and spiral wound configuration is most common for production of drinking water from groundwater. So, if the groundwater contains lot of TDS and other things, then spiral wound configuration is most commonly used. Also from groundwater, for surface water also we use this configuration in detail. Now, there are different effects which are there. So, earlier we have seen that the temperature affects the membrane performance of ultrafiltration, nanofiltration and microfiltration. For reverse osmosis case also it is the same, because the temperature affects the water viscosity and as well as the membrane material also. So, we have seen with respect to cellulose acetate that temperature, there is the effect of temperature on the cellulose acetate material. So, similarly for different membrane materials there is lot of effect of temperature which affects the water viscosity also. So, if water viscosity gets changed, the flux also gets changed. So, the permeate flow increases as the temperature rises because the viscosity decreases with increase in temperature. The relationship between membrane materials, temperature, flux is specific to different types of individual products. A correction factor should be obtained from the manufacturers. So, that means the manufacturers have to provide the correction factor. So, we can always help the manufacturer if we can understand the problem and let them find the correction factor in detail. Now, and that will be there with respect to temperature. So, these correction factors a manufacturer have to report with respect to different temperatures. Now, what the service life of these membranes? So, the membrane fouling will be one of the major reasons for decrease in the service life of the RO membrane. So, any of these things may happen like deposition of silt or other suspended solids on the membrane. Then inorganic scale deposition may also happen, biological fouling because the pathogens, bacterial species, viruses etc. May get screened out, and also because organic material is also there. So, biological growth may also happen, interaction of organic constituents with the membrane may also foul the membrane itself. So, this is there. Excessive concentrations of iron and manganese, if they are present in the water and if they are oxidized. So, what will they do is that they will form precipitate and that will foul the membrane. So, this is there. Scaling will also occur as a result of increasing recovery, because the concentration of the limiting salts will increase to their solubility limit, and after that they will start precipitating. So, this is another reason for fouling or scaling. The most common scales of limiting salts are like calcium carbonate, calcium sulphate. Other types of are also possible. Scales may be formed because of the calcium fluoride, calcium orthophosphate, strontium sulphate, barium sulphate, amorphous silica etc. So, any of these things present beyond the limiting conditions, they may form scales. Within limiting scales or limiting salt concentration, under certain conditions they will also foul the RO membrane. Now, an additional negative impact will be because of the accumulation of solute that will form a boundary layer of high concentration at the membrane surface. So, this is additional negative impact which will always occur at the higher concentration level. The concentration at the surface of the membrane becomes higher than the concentration in the bulk feed, and this effect is called as polarization. So, we always try to see that this polarization is minimized in the RO membrane. So, this we have to see, and polarization, if it occurs, it will have following negative impacts which are discussed here. So, water flux is lower because the osmotic pressure gradient is higher. So, water flux is lower here. If this polarization is occurring, rejection will also be decreased, and solubility limits of solutes will exceed, and that will lead to precipitation and scaling. So, already these issues we have discussed. These issues can be taken care by pre-treatment of the raw water and some operational procedures that we can adopt to avoid these polarization and other fouling issues. So, this is possible. Now, what we do is that we will further understand the what are the factors which affect the RO membrane performance. So, there are many factors which affect the RO membrane performance, and we will try to analyze each of these effects. So, the typical parameters which affect the RO membrane performance include the what is the flow rate under which we are operating, what is the permeate flux that we are getting after the separation, then what is the amount of salt rejection that we are performing, and what is the recovery rate of water, because this is very important for industry also and for industry in particular. The differential pressure or the pressure drop for under which we are operating our RO. So, that is also important consideration, and then what is the actual transmembrane pressure which is beyond the semi permeable membrane, and then the different other performance may be clubbed together in the tendency of RO performance with respect to other parameters. Now, first we will understand the flow rate. So, in RO device there are three streams, the feed stream, the permeate stream and the reject stream. So, the feed stream is separated by RO membrane into permeate and concentrate stream or reject stream. So, this is there. So, already we have earlier discussed this, so we will not go further into this. Now, the permeate flux. So, the performance will depend upon the flow rate or any of these fluxes, concentrate or permeate, because and this will be dependent upon the pressure under which we are operating, as well as the different physico-chemical characteristics of the membrane itself. Now, the permeate flux is the one which we desire the most. So, permeate flux describes the quantity of permeate which is produced during the membrane separation per unit time and per unit RO membrane area. So, this has already been defined earlier also. Then there is a term which is called as salt rejection. So, it is a percentage which is describes the amount of solute retained by the RO membrane. So, this will be R is equal to Cp upon C average, and C average is like a concentration of in the feed concentration as well as concentration in the concentrate or reject system. So, both. So, we can take average of that, and Cp is the permeate flux concentration. So, through this we can find out that how much amount of salt has been rejected or retained on the before the semi permeable side. Now, the recovery rate is with respect to the rejection is with respect to salt, but recovery rate is with respect to water. So, recovery rate is defined as the fraction of feed flow which passes through the membrane, and this gives the idea that out of the total feed how much amount of permeate we are getting. So, we always want to be higher, so that the rejected stream is lowest possible, and this is very important for any industry. So, suppose any industry is treating 1000 liter of water. Now, out of that they will always want to recover maximum amount of water. So, they will always want at least 800 900 meter cube or liter of water is retained, and only 10 to 20% is going as reject. So, and that because they have to still manage that reject water, because that will contain lot of solute and its concentration is will be very high. So, reject water management is one of the very big issues with respect to reverse osmosis. So, that is why they always want to have the highest recovery rate possible. Now, what is the differential pressure under which we are operating? So, the pressure drop which is between the feed and the concentrate pressure during from like feed pressure and the concentrate pressure. So, that is called as the differential pressure or the pressure drop, and across the RO membrane. Then similarly, there is another term which is called as transmembrane pressure. So, transmembrane pressure is defined as the difference in pressure between the feed side and permeate side. So, remember this pressure will be the pressure is usually measured in bar or PSI and is the driving force for membrane separation. In general, an increase in transmembrane pressure will increase the flux across the membrane. So, we always have to see that what amount of transmembrane pressure we have to maintain, and depending upon that flux will be there. So, permeate amount of permeate that will be getting is highly dependent upon this transmembrane pressure which is applied. So, it can be defined as Pf plus Pc divided by 2. So, that means average we are taking minus Pp, where Pf and Pc are the feed pressure and concentrate pressure, where Pp is the permeate pressure which is there. So, this is how this is defined. Now, tendency of RO performance we will try to understand. There are many parameters of RO membrane. The main parameters include the average permeate flux, okay, that we get, because we always want this to be our higher side, and the how much amount of permeate production is taking place, what is the salt rejection, and if both are there, that determine the quality of permeate and amount of permeate. So, we always want the quality of permeate to be best possible with highest possible rejection, and the quantity of permeate we want to be higher. Now, these two parameters can be influenced by number of other parameters like feed pressure, feed concentration, temperature, etc. So, we will try to understand the RO performance with respect to these parameters. In addition, the salt, what is the limiting concentration of salt up to which it can operate well, otherwise precipitation of salt will start occurring, because it will reach the maximum concentration limit or limiting concentration. So, this is there. So, we always try to find out what is the solubility limit of the salt that we are separating, and in its simplest expression it is a function of permeate recovery rate. So, here it has been defined, the Ksp is equal to, Ksp is the solubility product, Ap plus is the concentration of salt cations in the water, and that is in moles per liter. Similarly, Bq minus is the concentration of anions in the water in moles per liter. N and M are the number of moles which are there. So, we can see here N and M, okay. And then R is the recovery rate in the decimal fraction. So, we can always find out. The expression is simplified here because it does not account for activity coefficients, etc. So, original equation is much tougher, but we can use this equation to find out the KSP, and through this we can find out the different limit up to which the solubility will be there, and if the limit is breached, then the precipitation of salt will happen, and under those conditions the fouling etc. will increase. So, this is the problem that will happen. Now, we will try to see the operating conditions and effect on the RO system performance. So, like if feed pressure, if we increase the feed pressure, then what will happen? Then the flux will also increase and rejection will also increase. So, this is there because the permeate flux is proportional to the net driving force. So, if feed pressure is increasing, the flux will also increase. Now, the solute permeation rate does not increase with pressure. So, this is there, but overall permeate flux will increase. As a result, the flux and the salt rejection both will increase with increase in the feed pressure. Now, the second is the suppose in the feed the amount of salt concentration increases. So, under that condition both flux will go down, rejection will depend whether increase or decrease. So, net driving force decreases, net pressure difference decreases because of the osmotic pressure conditions and when the feed concentration increases. So, at lower salinity, suppose like less than 400 milligram per liter, the salt rejection decreases due to the charged effect on the RO membrane. So, this parameter is dependent upon that what concentration range we are operating. So, depending upon that this may rejection may increase or decrease, but flux will decrease with increase in feed concentration. Now, if the temperature increases, so under that condition the flux increases, but the rejection rate decreases. So, permeate flux increases with temperature like 3% per degree centigrade rise in temperature, and this is because of the decrease in the water viscosity. So, this is there. Now, the solute permeation rate increases with temperature more than the permeate flux. So, that is why rejection actually decreases. So, because the solute permeation rate is the increase in the solute permeation rate is more than the water flux increase. So, that is why the rejection rate is decreasing with increase in temperature, but we are getting more amount of permeate. Now, if the concentrate flow rate is increasing, the flux and the rejection both will be increasing, and the reason is that at low flow rate the concentration polarization occurs, and as a result the concentration at the membrane surface will become higher, and under that condition the osmotic pressure will also increase, and because of that the flux will also increase and rejection will also increase. Now, when considering the changes in the feed concentration, the salt rejection increases with the increase in the concentration first, and it reaches a certain feed concentration value, optimum value in the range of 300 to 500 milligram per liter. Okay. And afterwards the salt rejection rate will decrease as the feed concentration increases, and the influence of pH of the feed solution on the rejection of solute is highly complex, and because of pH fluctuation may also affect the change of charge of membrane surface as well as the dissociation rate and state of the solute. So, the effect of pH is different, but with respect to salt this is shown here. So, we will now see the effect of pH. So, if acidic compounds are there, the acidity pH will be low, and the alkalinity will be high. So, and here the change in the rejection rate will be happen. So, the dissociation of acids at alkaline pH enhances the rejection rate. So, this is there, and this is because of the charge repulsion which occurs between the compounds and the membrane surfaces at under this pH range. So, this is possible at in the alkaline pH condition. So, there are the effect of pH is highly complex, it cannot be generalized that much, but still we can understand it better. If basic compounds are there, so under if pH range is acidic condition, we have the rejection rates will be higher, and if the pH range or alkalinity is lower, then the rejection rate will be lower. So, under high alkalinity condition, the rejection rate will be lower. The dissociation of alkyne compounds at acidic pH range increases the rejection. So, that is why we can see that rejection rate becomes higher in the acidic condition if basic compounds are present, and this is because the charge repulsion occurs. So, this is the same as if acidic compounds are there, rejection rate is higher if the pH range is alkaline, whereas it is vice versa for basic compounds. So, this is how we can see the effect of whether acidic compounds are present or basic compounds are there, but still we can understand this more if we understand the water chemistry, the salt chemistry and the membrane chemistry. So, all have to be mixed together for better understanding, and so this is more complex, it is only simplified here for better little bit understanding. If suppose silica is present, then the rejection rate is lower in the acidic pH range and it is higher in the alkaline pH range. So, if amount of silica is more in the water, an increase in pH modifies the ionization of silica from silica acid to silicate at the higher pH condition, and therefore, it increases the rejection rate. So, this is why in the alkaline pH range the rejection rate of with respect to silica is higher. If boron is present, again in the higher pH range it is more rejected. So, increase in the pH modifies the ionization of boron from boric to borate and therefore increasing the rejection. So, we can go for finding out what are the different ionized species of different compounds under different pH conditions, and by understanding the type of membrane and its chemistry or orientation under different pH range, we can find out whether rejection will be there or not, and vice versa we can do the opposite, that we know that okay, some chemical is present in the water and what is its natural pH. So, its natural pH is suppose acidic. So, we can modify or use the membrane in such a manner, we can select the membrane the one which will give the highest rejection possible. So, through these chemistries we can understand a lot of things for a reverse osmosis case. Now, we will try to solve one problem before ending this particular section, and this problem can be understood in a number of ways as we have discussed here, but still we will try to find out this solve this problem. Okay, so, a membrane having an area of 25 centimeter square was used to conduct an experiment at 25 degree centigrade to find out the water permeability and salt rejection. So, define this. The initial concentration in the inlet stream was 15 kg salt per meter cube. So, this is it is equivalent to 15 gram per liter. It was observed that the inlet salt recovery is too low and that it could be assumed that the salt concentration at the entering and exit feed solutions was equal. Now, the product stream is containing 0.5 kg per salt per meter cube of the solution with a flow rate of 3 into 10 raised to minus 8 meter cube per second. A pressure differential of 45 atmosphere is being used. So, we have to find out the solute rejection and the permeability coefficient of the membrane. So, this is what we have to find out. So, again this salt rejection and the water permeability we have to find out using this data which has been given here. Now, solving the total salt flux across the membrane can be calculated first. So, for doing this we know the flow rate has been given, the salt concentration in the solution or the salt density has been given and the membrane area has been given. So, through this we can find out. So, flow rate is 3 into 10 raised to minus 8 meter cube per second, already it is given, and it is also given that the salt concentration is 0.5 kg salt per meter cube. So, this is known, and the membrane area that we are using is 2.5 into 10 raised to minus 3 meter square. So, if we solve it, it will be 6 into 10 raised to minus 6 kg salt per meter square per second. So, this is how we will solve it. So, this meter cube is going off and we are getting these results with respect to salt flux which is there. Now, to find out the rejection, the salt concentration in the inlet stream, salt concentration in the outlet stream divided by salt concentration in the inlet stream is found out. Now, these values are already given 15.5 and at the this is again 15. So, if you solve it, it is 0.967 is the answer. Now, it could be assumed that the permeate flow rate is predominantly water. So, if we assume that only water is going through, then we can find out the water flux. So, using this assumption, we can again the flow rate, water density divided by membrane area. So, we can find out the water flux. So, again the values are given here. So, we know the water density and this is the flow rate of the water. So, meter cube. Density is well known for water. So, we can find out in terms of kg. So, we have 1.2 into 10 raised to minus 2 kg of water per meter square per second. So, this is water flux is known. Now, to find out the permeability coefficient which has been given, we need to find out the osmotic pressure on each side of the membrane, and this can be known if you know the concentration. So, concentration is also known. So, we can find out the osmotic pressure on each side and then the total pressure which is applied. So, through this we can find out the net driving force. So, for finding out this permeability coefficient, we need to know the net pressure as well as the. So, for finding out osmotic pressure first, we use this equation. So, already it was defined earlier. So, this is 15 gram per liter. Okay. So, now we are converting this into this particular equation. So, gram per liter, and we know we use appropriate unit of R, so that everything goes off and we have the actual answer in atmosphere. So, we are using this particular unit and we can see here that everything Kelvin is going off, moles are going off, okay, and then we have gram per liter. So, liter is going off. So, we are converting the this is gram mole, okay. So, we have gram also going off. So, every unit will go off and ultimately we will be having 12.54 atmosphere. Similarly, we can find out for the second condition where only 0.5 gram per liter of the salt concentration is there. So, we have 0.42. So, this way we know the difference in the osmotic pressure is there. So, that from what we do is that we subtract 0.42 from 12.54. So, through this we can find out the delta pi. So, delta pi will be equal to 12.54 minus 0.42 and we will get the answer 12.12 which is used here. Now 45 atmosphere has already been shown. So, and if we subtract this from here, we get the net pressure difference which is applied, and if we know, then we can find out the permeability coefficient, because the tentative water flux is already known to us and we have calculated here previously 1.2 into 10 raised to 10 raised to minus 2 kg H2O per meter square per second. So, if perform this calculation, we can find out the permeability coefficient for the our membrane that we are using. So, it will be 3.65 into 10 raised to minus 4 kg water per meter square per second per atmosphere. So, this is what we have to report for that RO membrane if we are using. So, and already we have found the rejection rate. So, this is how we can perform the calculation. Many references have been used in all through. So, you can always refer to the references for better understanding this RO process and the membrane operations in general for water and wastewater treatment. Thank you very much. So, any of these references can be used. Thank you.